Hello everyone, my name is Liao Meihao, a PhD candidate from Beijing Institute of Technology. The title of our research paper is Efficient Personalized PageRank Computation, a Spanning Forest Sampling-Based Approach. First, we will introduce the problem definition. Personalized PageRank is an important measure of importance. Specifically, pi-st measures the importance of T with respect to S. The personalized PageRank is defined based on the probability transition matrix. It considers paths with all possible lengths. The PPR matrix is defined as the inverse of a matrix, and it can be expanded into Newman series. The personalized PageRank value pi-st equals the st element of the PPR matrix. A naive Monte Carlo method to estimate personalized PageRank is to simulate alpha random walk. Alpha random walk is a type of random walk that at every step, it stops with probability alpha and jumps to a random neighbor of the current node with probability 1 minus alpha. Then the personalized PageRank value pi-st can be explained as the probability that an alpha random walk starts from S, stops at T. Based on this Monte Carlo method, if we want to know all pair personalized PageRank, we will need to simulate alpha random walk from every node. Here is an example of such simulation result. We walk many steps, but we care about only the endpoint. For example, the node 1 stops at 3, the node 6 stops at 5. We only care about the endpoint. When alpha is small, the expected length of the random walk will be very large. Current algorithms are inefficient when alpha is small. And recently, there are applications requires the cases when alpha is small. Such applications include local graph clustering and graph embedding. When alpha is small, a larger part of the graph will be explored. Thus, the performance of the applications will improve. So next, we can see an intuition of our spanning forest-based approach. The random walk result in the bottom left of the slide is equal to the random walk result at the bottom right of the slide. The rooted spanning forest can be regarded as a summary of the random walk results. For example, in the rooted spanning forest, the node 1 is rooted in 3. Here, we refer to a node rooted in one node, is that a rooted spanning forest can partition the graph into several connected components, and each connected component has a node as a root. For example, the left connected component has node 3 as its root, so the node 1 is rooted in 3, is equal to the random walk results at the left. The node 1 stops at 3. This is an intuition of our result. Next, we will propose our solutions. Matrix tree theorem is a well-known result lies at the heart of the graph theory. It states that the determinant of the submatrix of the Laplacian matrix equals the number of spanning forests. Here, the submatrix of the Laplacian matrix refer to the matrix obtained by deleting the width row and width column of the Laplacian matrix. And our results generalize the well-known matrix tree theorem to a personalized PageRank case. From spanning tree to spanning forest. Here is some examples of spanning forest. And specifically, if we define a probability distribution over all random spanning forests, for example, the probability distribution is the the probability distribution is proportional to alpha divided by 1 minus alpha to the power of the number of roots. We will prove that the personalized PageRank value pi st equals the probability that S is rooted in T in a rooted spanning forest sampled from this distribution. Formally, we can define a matrix that is exactly the inverse of the PPR matrix. We refer to this matrix as the beta Laplacian. Beta Laplacian is equals the beta D, the inverse of beta D multiplied by L plus beta D. Here beta equals alpha divided by 1 minus alpha. We propose a personalized PageRank matrix forest theorem, and specifically, the PPR value pi st equals the inverse of a matrix. And according to Cramer's rule, this inverse can be written as 2 determinant. And the determinant in the denominator of the result can be represented as the number of all rooted spanning forests, and the determinant in the numerator of the result can be explained as the number of rooted spanning forests in which S is rooted in T. This is a generalization result of the well-known matrix tree theorem, and the proof is similar to the matrix tree theorem. For example, now we have 2 spanning forest-based estimators. When we sample a spanning forest according to the probability distribution, we have a basic estimator that we only need to look at the spanning forest and to see whether S is rooted in T in the sampled spanning forest. The estimator is an indicator variable that XST equals 1 if S is rooted in T. And the improved estimator is that we only need to see whether S and T are in the same connected component. And the estimator is built by XST multiplied by a conditional probability. The 2 estimators are all equal pi st. The relation to rooted spanning forests brings novel and effective algorithms. The drawbacks of traditional algorithms is that we have many reduplicative steps. Second is that we only care about the endpoint of the random walk results. The walk we pass is not important. There are many efficient algorithms to sample spanning forests or spanning trees. Among them, the most effective is the Wilson algorithm. And we iteratively run random walks and erase the loops. And finally, we will get a spanning forest. So we propose a modified Wilson algorithm to sample a spanning forest based on the probability distribution we defined before. The process of the modified Wilson algorithm is the following. First, we fix an order of nodes and initialize the spanning forest F as an empty set. Then we run alpha random walk following this order and add the looping ratio to F. Then we run alpha random walks outside from F until it stops or hits F. If the random walk stops, the node where it stops will refer to as a root. And the algorithm will terminate when F spans all nodes. The advantages of the new algorithm is that first, an alpha random walk stops faster and faster as the algorithm runs. Because the random walk runs, the F grows larger and larger, and it's easier to hit F as F grows. The second is that every step of the trajectory except loops counts. We will no more get some reduplicative steps. And the third advantage of the algorithm is that it's more efficient when we consider the variance reduction techniques. Next, we introduce two applications of our proposed algorithms. The first is a single source personalized PageRank query. The problem answers the personalized PageRank value pi SV for all v belongs to the node set. There is an efficient deterministic local push method called the forward push. During the forward push procedure, the following invariant is maintained, that the personalized PageRank value pi SV equals the current estimation plus an error. And the state-of-the-art algorithm uses Monte Carlo method to estimate the error, so we can obtain a more precise result. For a single source query, it requires to simulate random walks from all nodes. This is exactly what we optimize. The state-of-the-art algorithm mostly adopts the bidirectional framework, and most current works focus on optimizing the deterministic direction. Little work make efforts to the randomized direction. Our work improves the efficiency of the randomized direction, thus gives the best approximation algorithm for single source query with approximation guarantees. The second application is a single target personalized PageRank query. The result is similar to the single source personalized PageRank query. Next, we will introduce the experimental results in our paper. The first result indicates that when alpha is small, random walk becomes harder to stop. Walk small steps, exploring larger part of the graph. Former algorithms are far from efficient, and our proposed algorithm are insensitive to alpha. We can see from the picture that when alpha becomes small, the running time of other algorithms all grows very rapidly. And our loop erased walk random walk based algorithm grows slowly. So our algorithm is significantly better when alpha is small. The second experiment is to evaluate the single source personalized PageRank query compared to the state-of-the-art computators. It can be seen that there is a significantly speed up over the state-of-the-art algorithms in terms of both query time and empirical error. And the best empirical error is obtained via the improved estimator, where we refer to as speed LV in the picture. When alpha equals 0.01, this is a relatively small alpha, and the speed up over the state-of-the-art algorithms is more in this case. And the third experiment is a single target query. We can see that when alpha equals 0.2, our algorithm degrades to push when alpha equals 0.2, and our algorithm obtain a speed up when alpha equals 0.01. Here is a take-home message. Personalized PageRank can be explained through the weight of rooted spanning forests, and the relations to rooted spanning forests brings efficient loop-erased alpha random walk sampling algorithms. Thanks for your listening.